Hi, I'm Jan Witkowski. I'm Director of the Banbury Centre here at Cold Spring Harbour Laboratory, and this is the final day, final afternoon of the 79th Symposium, 79th Cold Spring Harbour Symposium on Quantitative Biology. And this year the topic is Cognition. I'm very pleased to have with me Daniel Wopert from the Department of Engineering at the University of Cambridge. So a good question to start with, what's someone from the Department of Engineering doing at a biological symposium?
Well, please don't tell anyone, but I wouldn't pass first year engineering. So I'm a medical doctor by training, but I got much more involved in using computational ideas to understand the brain. Mm-hmm. And so over the years, I've used sort of control theory signal processing. So when the engineering department wanted someone to do bioengineering, they thought they'd hire a biologist with an interest in engineering rather than an engineer with an interest in biology. And that's been very productive.
I was going to say that's much more, that's the way around, the way around it should be. Yeah. So what sorts of problems interest you in the department?
So I work on how the brain controls movement. That's my fascination, and the reason I think movement's so important is that effectively it's fundamental to our existence. That the only way we can affect the world around us is through the contractions of muscles. There's no other way to improve your survival. Mm-hmm. So it's important to remember that things like sensory, memory, and cognitive processes are only important to drive or suppress future movement. So the beauty of working on movement is you have to work on the whole system. It's the final output.
Mm-hmm. Mm. So that, maybe I'm jumping ahead to the end of the conversation, but so does that imply then that you feel the brain, the primary function of the brain and all its systems of controlling movement and the evolutionary pressure on the brain is actually through controlling movement?
All through evolution. So I mean, I would say there's no point laying down memories of childhood or seeing the colour of a rose if it doesn't affect the way you're going to move later in life, because it can have no evolutionary advantage. So effectively, it's all driven by movement. And so, although you can study things like vision or cognition in isolation, it's really important to remember that the reason to have these processes is to drive the actions. And another thing beautiful about studying movement, it's a very hard problem, and we can really appreciate that if we look at how well we do building machines which can do what we can do. So we can build machines to play games of chess, and they can beat grandmasters, but we can't yet build a robot which can manipulate a chess piece with the dexterity of a 5-year-old child. So it's a very challenging mathematical and computational problem, and if we could reverse engineer the brain, not only could we understand it from an intellectual curiosity point of view, and to help people who have movement disorders or for rehabilitation, but we could also hopefully build better robots as well.
So I don't want to lead us down the robot line,
no,
when I think of robots or robotic arms, I think of those big ones on welding on a car assembly line. They seem to do okay.
They do okay. So if you want a robot to do a very single task, you can get the robot to do that one task through many years of hand tuning it. What you can't do is, once you've done that, it's going to do another task. So what we're particularly good at is flexibility and manipulation tasks, where these big robots are really designed to do one specific thing. And so what we really hope to do is understand the learning algorithms, which we think are really fundamental to allow machines to learn anything they want to learn.
So how do you set about trying to learn those algorithms experimentally?
So our approach is on the human. We're really interested in the algorithms, and we then hope that those algorithms will be understood at the implementation level in the brain by other labs who do more animal type research. We work on undergraduates, and we bring them into the lab, and we have robotic interfaces and virtual reality. And by controlling what people see, what they feel, and giving them new skills they have to learn, we can begin to tease apart the algorithms that they use in their brain when they learn new skills.
Can you give an example of what one of those tests
Sure.
looks like?
So the sorts of things we might do is we might put people into a very unusual situation where you hold a robotic interface and it produces a force on the hand as you move which you've never experienced before. So we particularly want to make sure that you give someone a new skill to learn. And I'll just give you a result of one of the experiments we've just done. We were fascinated why people follow through in sport. So, why is it when you throw a ball or you hit a ball in tennis or in golf, people tell you the follow through is so important when the action's all over by then. Right. But what we've trying to understand is how do you activate different motor memories. So we have different skills we learn. We know how to ride bicycles, drive cars, and we access different motor memories at different times. So what we've just really found out is that the way you activate a motor memory depends on not only what you've done in the past, but what you're going to do in the future. So if you have a consistent follow through after an action, you store that in one motor memory. Whereas if you have different follow-throughs, you store them in different motor memories, and therefore you don't consolidate them. And so what we've shown is part of the reason why you want to follow through is to store everything into one motor memory. Right. And the way we do that is by using our robot to perturb you, and then have to make different movements after that perturbation, and study learning.
And does sticking with the follow-through thing, if you get the right follow-through, does you presumably require the right pre-stroke.
Pre-stroke,
The action to
absolutely. So what we've shown is that about half a second before the movement determines which motor memories you access. So things happening more than half a second in front of the movement don't determine which motor memories you can access. About half a second before to probably, we don't yet know the time course, half a second after the movement is the critical period. So basically the near future and near past determine how you activate motor memories. Which is an interesting time period now. Why it should be that half a second that is important, we yet don't know, and that's an interesting question for us to answer.
How broadly applicable do you think this is across? And I was talking to Corey Barton this morning about the reversal in her C. elegans, and does a C. elegans in some way make use of this sort of?
That's a very good question. I don't know whether C. elegans can learn quite as many things as humans can. So we're able to learn many skills. So the activation of memories, they have a set of repertoires. I'm not an expert, and I would hate Corey to tell me off after this. Right. So I don't know whether they can store many motor skills, but they certainly can switch between their skills, and the way they do that seems to be based on these neuronal models that she's developed.
So what things have intrigued you most in your the work?
So what's really driven me is trying to understand how motor system works, particularly from the point of view of what we call noise. And when I talk about noise, I don't mean sound. I mean the variability we have in our senses and in our muscles, effectively. So one thing which characterizes humans compared to robots is how incredibly variable we are. And if I put my hand under a table, try to localize it with my other hand, I can be off by centimeters. If I try to play darts, I have huge variability, yet we're very skilled. And so one of the things we've been working on is how does the brain get round the problems of that variability? And it turns out one of the models we developed suggests that because we have so many ways you can do a task, if I ask you to point to your nose, you could do it like this, but you could choose to do it like this or any way. But most people will do these tasks in very similar ways. And we think the reason people do that is it's somehow the optimal way to move so as to reduce the bad consequences of this variability. And so it turns out that this variability makes us move the way we particularly move. And that's rather nice. It means we can generate models or predict how people should move and how, if you move in different ways, you're going to be less accurate, for example. So I've been driven very much by those sort of noise models and what are called Bayesian models, which say what we have to learn about to perceive the world is statistics. And as you go around the world, you learn about the statistics of the outside world, and that's really important to allow you to estimate and predict the future.
So if you take 1,000 people and they're all right-handed, and they've all got the right number of fingers, and that's the thing, and you ask them to touch their nose, how variable is the path by which they do it, or?
It's not very variable. I mean, we've certainly done it for reaching movements, picking things up. It's very similar. We all walk roughly the same way. We all reach the same way. Now, you don't have to. Out of the infinite number of ways you could reach to pick something up, there are many ways we don't choose. And so it's interesting to ask why we choose these particular solutions. You know, the way we walk is very stereotypical now. People like Monty Python made their early career by violating normal biological motion, which somehow is funny to us.
Right.
But the fact that we always say tells us something about the way the brain is organizing these movements.
And how early, presumably a baby learns these things.
Yes.
And does it learn by imitation, or is it?
No, I think it can learn.
Internally?
I think imitation helps, but I think it's internally learned. I mean, I think we start off with a right approximation, but as you grow, and in fact the noise is very big, the variability is much bigger in babies. So for example, the way they start moving their eyes is very different to the way adults do, and only by age of 3 or 4 do they start having eye movements similar to the way we move our eyes. We move our eyes almost all the way to a target. They, because they have so much variability, make little small steps. Because if they try to get there in one go, they'd have so much variability they'd be hunting around all the time. So we think these are probably learned throughout experience. And the real question is, why is it that I'm not as good as Tiger Woods at golf?
Yes.
It could be that he's found the optimal solutions and I'm just not good at them. I have to keep practicing. But what I probably believe is that we have different levels of variability. And I've just got a higher level of variability, and therefore whatever I do, I can never be as accurate as him. And some people are just born lucky in terms of that variability.
Can you test that? I mean,
it's a little hard to test because it's hard to separate experimentally the person's optimal versus those with noise. We're thinking of ways to do that. It'd be wonderful to sort children to say, right, you go into the piano and you should be on a big drum. But that's a little harder. That's a dream for the future.
Yes. Okay. Well, I think on that dream for the future we'll stop. Thank you very much, Daniel.
Thank you.